Hello everyone and welcome to this Tizen webinar. My name is Sanjeev. I am from the open source group of Samsung Electronics. The topic for this webinar is Tizen Native Application Framework. During this webinar, we will learn about the concepts involved in developing native mobile applications for Tizen. Details about the different types of API, event handlers, application lifecycle model will also be provided, which will help you to get started with writing native applications for Tizen. Tizen is a Linux-based open source operating system capable of powering multiple device categories like mobile, wearables, television, and in-vehicle infotainment systems, to name a few. It is jointly developed by major technology companies like Samsung, Intel, and many more. Multiple devices like the Samsung Gear 2, Gear 2 Neo, and Gear S are based on Tizen and are already available to consumers. Tizen enables application developers to develop and distribute applications which can be downloaded and executed on Tizen devices. It supports three types of applications: web, native, and hybrid. Web applications are developed using popular web standards and technologies such as HTML5, JavaScript, and CSS. Tizen provides best-in-class implementation of the W3C specifications. It also provides access to device-specific hardware features through the Tizen Web Device API. Using this API, web developers can leverage their web application development skills and bring new applications or bring existing applications to Tizen with very little effort. Tizen native applications are very similar to conventional Linux applications developed using C or C++ programming languages. However, they run in resource-constrained hardware environments like mobile phones and wearables like the Gear. They can also access device-specific hardware features like camera, accelerometer, and GPS. The Tizen native API helps application developers to handle these conditions. During this webinar, we will focus on the concepts and details regarding the use of native API to develop mobile applications. Tizen also supports the concept of hybrid applications where web and native API can be used to build different parts of the application. For developing both native and web applications, Tizen provides a software development kit, also known as the SDK. The SDK contains all the tools that developers need to build, debug, test, and package an application for distribution. In addition, it contains an extensive collection of sample applications and documentation. Tizen SDK can be downloaded for free from the link shown above. Before discussing the concepts involved in writing a native mobile application for Tizen, let us take a look at the native application architecture. Tizen applications need to use different hardware features provided by the device depending on the tasks they perform. The hardware features available in the device might vary based on the device type. The Linux kernel and device drivers manage the system hardware and provide an interface for the core layer to access the hardware features. The core layer consists of a set of frameworks which handle the interaction with the kernel and device drivers. Each framework performs a very specific function like telephony, multimedia, display system, etc. These frameworks are part of the Tizen platform and are built using a combination of open source and custom-built software components. The core layer abstracts the complexity of handling a diverse set of frameworks by providing the native API. The native API provides a comprehensive set of functions that cover a broad range of requirements most commonly needed by native applications. The functions are logically grouped based on the core layer frameworks like location, sensors, telephony, and multimedia. The native API provides a uniform way of accessing the core layer functions through consistently named API. The different hardware features are represented as resources which can be accessed using handles. Using the native API, applications can access the underlying hardware features in the device. With this background information, let us take a look at native applications for Tizen. Tizen supports two types of native mobile applications: UI application and service application. UI applications have a graphical user interface and handle user interactions. They respond to the user inputs and perform tasks and provide the feedback to the application via callbacks. Typical UI application examples are social networking apps, games, and productivity apps. The user interface for Tizen native mobile applications is written using the Enlightenment Foundation libraries, popularly known as EFL. EFL is an open source suite of libraries that is well maintained by a strong open source community. It has been in active development since 1997. EFL provides a lightweight, fast, and modern UI framework to build native applications for Tizen. The Tizen SDK provides numerous examples of how to use EFL to create beautiful UI applications. Service applications, on the other hand, do not have a graphical user interface. Service applications provide a specific service that can be used by a number of other applications, thereby reducing effort and duplication across applications. Typical service application examples include background music player, file downloader, and email clients. Both UI and service applications have well-defined lifecycles and states which control the application behavior. Both can also use other open source libraries supported as part of native API. One of the most important parts of the native application is the Application Framework API, which defines the lifecycle of an application. Let us take a look at the Application Framework API. Application Framework is the core layer framework which provides key functionalities required to build a native mobile application. The Application Framework provides API for handling application lifecycle, launching other applications, getting information about available applications and packages in the system, using the notification area and application home screen icon to display application updates, creating shortcuts to the application on the home screen, communicating with other applications, and handling database interactions. Of the given set of API, Application Lifecycle API is an integral part of all Tizen native applications. The other API can be optionally used by applications based on its requirements. A Tizen native application is in the ready state when it is launched by the user. In this state, the application registers itself with the application framework. After the initialization step is completed, it moves into the created state. In this state, the application has completed the steps needed for handling its lifecycle and system events. The application framework is now ready to control the application. The application framework moves the application into the running state. In this state, the application is performing its task. It is important to note that in the running state, the application is in a main loop. The core idea behind main loop is that the application will sit in a loop and check for events, handle timers, and other services. The main loop is in dumb and will not consume CPU unless there is work to do. It will sleep and consume no CPU time until some event happens. The main loop wakes up whenever there is an event to handle, like a user touch event or a network response or a new push notification. Other examples of events include system events like change in orientation of the device, low battery, and low memory events. In the case of UI applications, the user can press the home button or switch to another application, for example, handle an incoming call. These actions make the currently active application move to the background and thus invisible to the user. In such cases, the application framework will notify the currently active application about the event and move it to the paused state. In the paused state, the application can limit itself to perform only the tasks essential in the background state, thereby conserving system resources. Finally, when the application is terminated by the user or due to low memory conditions, it moves to the terminated state. All applications are in the ready state when they are launched. UI applications enter the ready state by calling UI app main. Service applications enter the ready state by calling service app main. In this state, the application initializes the callbacks to receive notifications from the application framework. These callbacks include lifecycle state change callbacks and system event callbacks. The application registers these callbacks with the application framework. Once the registration is completed, the application framework takes control of the application lifecycle. From the ready state, the application framework moves the application to the created state. Before the application moves to the created state, the app create callback provided by the application is invoked. This callback is used to initialize the application before the main loop starts. Typical operations in this callback would involve initialization of UI elements and setting up database connections. After the application returns from the app create callback, the application framework moves the application to the running state by calling the app resume callback. In this state, the application is performing its normal operations like interacting with the user or doing network operations. In the case of UI applications, the app pause callback is invoked before the application can move into paused state. Application can release resources not currently used. An application in paused state can return to running state, and in this case, the app resume callback is invoked again. Finally, an application can move to terminated state by invoking the UI app exit or service app exit API, or the application framework could terminate the app to handle low memory conditions. In either case, the app terminate callback is invoked before terminating the app so that the app can perform necessary cleanup. In addition to the lifecycle event callbacks, the application can also choose to register callbacks to handle system events like low memory, low battery, change of device orientation, change of language and region formats, etc. There are different actions that the application can take depending on the type of system event. For example, writing data to disk can be done when low memory callback is invoked. CPU-intensive tasks can be stopped to conserve battery when the low battery event is received. The application's UI layout can be refreshed to adapt to the new orientation when orientation change event is received. This completes our overview of the application lifecycle and system events. Let us take a look at how all the above concepts can be used by means of an example. Here, we have a code block that explains how to declare the different lifecycle callback event handlers for a native application. As you can see, each of the states have their own handlers, like app create, app pause, app resume, and app terminate. The state transition occurs after the completion of these callbacks. Next, we have the code block that explains how to declare the system event callback handlers. You can declare callbacks per system event. Once the lifecycle and system event handlers have been declared, the next step is to initialize them with the application framework. In the main function of the application, we initialize the data structures defined by the application framework, namely UI app lifecycle callback _s and app event handler _h. Please note that the application is now in the ready state. For lifecycle events, we simply assign the function pointers. For system events, we add the event handlers using the UI app add event handler API. Finally, the application moves to the created state by calling the UI app main function, providing the lifecycle handlers to the application framework. After this call, the application moves to the main loop with the application framework taking control of the lifecycle of the application by invoking the appropriate lifecycle and system callbacks. This completes our overview of the application lifecycle. The details provided so far regarding application lifecycle mostly apply to both UI and service applications. While designing service applications though, there are a few key differences to remember. In the application manifest file, we need to set the component type parameter as svc app to distinguish service applications from UI applications. If we want the service application to be restarted in case of any error, we need to set the auto restart parameter to true. If we want the service application to be started when the device boots, we need to set the onBoot parameter to true. The above two parameters will ensure that the service app remains available for handling requests. Service applications do not have a user interface and consequently no paused state, since they always execute in the background. Also, the API signatures for the service applications have a service underbar prefix instead of a UI underbar prefix used for UI applications. If application developers handle these differences, they can create service applications which can be used by all applications in the system. Now that we have discussed about service applications, let us look at how service applications can share their functionality with other applications. Also, we will look at how other applications will make use of the functionality exposed by service applications. One of the popular features available in most modern mobile operating systems is the ability to use the functionality offered by other applications in the system to complete a given task. For example, take a common task like sending email. If every application had to write its own code for handling emails, it would be very inefficient and leads to duplication of effort. Instead, if an email application can share its sending functionality and make it available to other applications in the system, then other applications can make use of only this function without having to duplicate the effort. App Control API helps Tizen native applications to export selected functions to be used by other applications. There are two ways to use the functionality provided by other applications. Explicitly launching the other application's functionality by using application ID and the operation we want to perform. Implicitly launching the other application's functionality by specifying the operation, URI, or MIME type and letting the user decide the application to complete the operation. Let us explore these launch types and API further. Applications can be launched explicitly if the application ID is known beforehand. This can be useful for cases where we would like to make use of the functionality provided by preloaded applications like browser, calculator, etc. In order to do an explicit launch, the following steps are required. Declare an app control handle. Initialize it using the app control create API. Set the operation to be performed on the handle. In this case, default would mean that we simply want to show the calculator. Set the predefined application ID string using the app control set app ID API. Trigger the launch request using app control send launch request API. Get notified of the result of the launch via a callback. But there are some cases where the same functionality could be provided by multiple applications. For example, there could be multiple email providers. In such cases, we would like the user to be able to select the appropriate choice for completing the launch request. This is handled via implicit launch. Applications can be launched implicitly for cases where there are multiple applications capable of providing the same service or when the application ID is unknown. In order to do an implicit launch, the following steps are required. Declare an app control handle. Initialize it using the app control create API. Set the operation we want to perform on the handle using app control set operation. Set the URI or MIME type format string using app control set URI or app control set MIME. Trigger the launch request using app control send launch request. Get notified of the result via a callback. If there are multiple applications capable of handling the launch request, the application framework will pop up a dialog with a list of choices from which the user can choose. So far, we have discussed how one application can invoke another application using implicit or explicit launch. If the application wants to export its functionality so that other applications can use it, we need to implement the following. The first step is to declare the MIME URI types and operations in the application manifest file using XML tags. The operation tag specifies the action to be performed. The MIME tag specifies the MIME types that will be handled by the application. The URI tag specifies the URI to be used to perform the operation. The application framework calls the application's app control callback when the application is in the running state. This callback is passed the app control handle, which contains the reason for the launch. For example, the application can be launched to open a file in order to handle the request that has been sent by another application. In the above cases, the application is responsible for checking the content of the app control and responding appropriately. App control methods like app control get MIME and app control get URI can be used to get the launch parameters to take the corresponding action. This completes our overview of the application lifecycle, UI and service application details. Now, let us look into some of the other API features provided by the application framework. Notifications are indications to the user about events of interest regarding applications. The application framework provides a simple notification API for applications to post notifications. Applications can post notifications in two areas. One is the standard notification area and the other being the ongoing notification area. Based on the type of notification required, the API provides multiple options to set the icon, the LED color, the text message, among other parameters. Ticker is the type of notification that appears on the screen for a short while and gets stacked in the standard notification area for later use. Quick panel notifications allow the user to see all notifications and their content in a short form in the quick panel. The listed notifications consist of completed tasks that have been run in the background in addition to the messages that the user is yet to read. A badge notification can be used when a non-urgent notification occurs. The badge shows the number of notifications as a small icon. It is generally added on the main application's menu icon. Different sounds can also be set to indicate application-specific notifications. Using the notification set launch option API, users can choose the application to be launched when the notification is selected by the user. Data control is a mechanism for exchanging data between applications. All applications can request data shared by other applications using data control. However, only service applications can provide their own data. There are two types of data controls. One is data control SQL, which allows you to use a SQL type data control to access the data exported by other service applications. You can also define a SQL type data control provider to export specific data from your service application. The other type is the data control map. which allows you to use a key value type data control to access the data exported by other service applications. You can also define a key value type data control provider to export specific data from your service application. Bundles are string-based dictionaries that store abstract data types. They can be used to pass data to and from Data Control API. Apart from simpler data management, they also provide API to encode and decode data. The Tizen SDK provides the complete development environment to develop Tizen native mobile applications with extensive documentation and programming guides. There is a large collection of sample applications provided that explain the usage of various native API. We have so far covered the basics of Tizen native mobile applications, the application lifecycle, the differences between UI and service applications, and how to use the App Control API to invoke the functionality offered by other applications. The amount of API in the application framework is quite extensive. I hope this session would have given you enough information to help you get started with writing applications for Tizen mobile devices. Thank you for your participation and hope to see you in another Tizen webinar.